Welcome back. I have recorded the answers in a separate video because it requires more explanation, and I didn't want to just continue doing it because there's just too many elements and I want to take my time. So I recorded the answers to the questions that I gave you on a separate video. So the first element that we had was calcium, right, on our list. Now there is only one element on this list that is kind of an abnormality. Even if from everything I've explained so far, you may have not got the right answer, partly only for identifying the valence orbitals for, I would say, titanium, okay, Ti. But let's do that last. The first element we had was calcium, okay, and its atomic number is 20, right? And that means we got 20 protons and 20 electrons, right? As always, we pay our attention to the electrons when we write our electronic configuration. Calcium, of course, is in the S band in the fourth row, so we got quite a few candidates ahead of it. So 1s, 2s, 2p, 3s, 3p, and 4s. No problems, right? Because it's only when you go past your 4s things start to get a little complicated. But up until calcium, yeah, we're good. All right, so that means we need 20 electrons, so we start from left to right. Calcium, of course, S can take 2, S can take 2, P can take 6, S can take 2, P can take 6. Now we stop here and we count. We notice there is 18 electrons all in all, but we need 20, so we put 2. And if you go back and look at the Roman numeral for calcium, it's 2A, right? That means it's got 2 valence electrons, so let me get a different color. There's no need to rush, okay? If you don't understand it during one of our group sessions, you're welcome to ask me questions, okay? So that's my valence orbital because there is no other orbital past 4s. It's the last one, and it also doesn't have any other 4 tied to it, so it's a valence orbital, right? It's a singular valence orbital. So that's the correct electronic configuration, and I've identified what the valence orbital is for calcium. All right, the next element in line is chlorine. So let's go get our pen. So chlorine, I believe it's 17 periodic table atomic number is. So 17, that means we got 17 protons and 17 electrons. As always, we focus our attention on the electrons for the electronic configuration. So it will be 1s, 2s, 2p, 3s, and 3p, because chlorine is in the p band in the third row. Does it make sense? I mean, that's, if you keep saying the way I'm saying, you will never even forget, or it will always seem to make sense to you. Chlorine is in the third row in the p band. That's why we end up with 3p as our last one. Well, we need 17, so let's go get a different color, maybe a black, be consistent. So we need 2 electrons in S with no problem in 2. So always when we get to the last, we need to figure out how much do we have so far. We have 12, which means we need 5 more, and that's 5. Okay, let me get a different color again. All right, so far we don't need to flip anything, everything is good. And then if you look at the Roman numeral for chlorine, it's 7A. Okay, and it seems to make sense. As I said, you look for the last orbital, and if there's anything else with the same row number, then they all would together be the valence orbital. So in this case 3p, but then I also noticed 3s is there. So there we go, and it seems to make sense that I am able to account for my 7a, which means how many electrons does chlorine can take, because it has to get to 8. That means it can have only one more electron to get to stable configuration. That means it's 1 minus. This is bonus. Okay, you don't, if you had not done this last part, that's all right. I didn't expect you to do it. All right, the next element, we are going to skip titanium and come back to the very end, because even within what I have explained to you, there is an abnormality or exception to it. So we're going to skip that. Let's just go to zinc. Okay, because every other element I have taught you falls under everything I have taught you except titanium. I didn't realize that. Okay, so zinc is 30. Okay, and zinc, I believe, is in the third row, kind of a weird third row in the D band, right? Because there's that's where we flip. All right, so I am going to write you actually the corrected version and see if you've got that, just in lieu of time and video spacing. I am going to just write the corrected version. This is what you should have had, and there's, so you should have had 2, 2, 6, 2, 6, 10, and 2. Okay, this is what you should have had when you're done. Now, if you're wondering, hey, can you show us just one more time? Absolutely, you probably expected that. So this is the corrected version. Okay, this is the uncorrected version, or the not the flipped version, because if you follow my periodic table sequencing from that one PowerPoint, this is what you should have had. Okay, to start off, this is what you should have had. But as I said, the 3's will go with the 3's and the 4 would come out, because that's the way the energy is sequenced. Now, if I had done this, it would be 2, 2, 6, 2, 6, 2, and 10. But as I said repeatedly, this might be the sequence, but because there is an energy fluctuation, we can have 4s is higher in energy than a 3d. So 3's must goes with 3's, and there is obviously no force, but it's got to go as an outlaw. Okay, so this gets flipped over here, right? And that's what leads us to this configuration right here. Does it make sense? Because that's how the energy band is, and as I said, due to some reasons, they put the D in the fourth row. Now, if they had started it in the end of second row, this would have fixed the problem, but this would have caused more problems as we do this. So this is the corrected version. The one in the black is the corrected version, and the one in the blue is the uncorrected version for energy sequencing. Okay. Now, if you leave it like this on the test, the second one, it's in blue, I would not award any points for it, because that is incorrect. Okay. Like a Sarah with a H or without a H, they're two different people. Okay, you may decide to call both people the same, but they're not the same names. Okay, the one, a Sarah with a H at the end, and the Sarah without a H, they're both Sarah, but they're not the same people. Okay, so just because you have the uncorrected version does not mean that is the correct answer. I will not award any points for it, because you are misrepresenting chemistry at that point. This is a starting point, the one in the blue, but the one in the black is the corrected version. So when I ask you to write the electronic configuration, you cannot write this and expect me to say that you did do correct chemistry. I will not award any points for it. This is, to me, is correct chemistry, and that's how it should be represented. Okay, now if you notice, why 4s is the abnormally sitting one outside, so that has got to be our valence orbital, because that's another one of the questions I posted you. So if you go back, there we go, that's our valence orbital. And if you look right on top of zinc, I believe it reads 2b. That means, what is zinc? Zinc is a metal, so it can only lose 2 electrons at the most it's a metal, so when metals loses electrons, we call it 2 plus. This is bonus, obviously, I'm retouching that concept, but that's how we do those. And I'm going to make another video for the remainder of the elements because I think it's already getting too long. So I'm going to stop here and then start my next video where I will address the remainder of the elements, including titanium, and why the valence is an exception there. Okay.